Welcome to Unit 1, Lessons 2 and 3, where we are going to learn about identities. This video addresses the fundamental identities, but by the end of this lesson, you would be able to use those fundamental identities to evaluate trig functions, to simplify and rewrite trig expressions in a form that might be more useful, and verify trigonometric identities. You have dealt with identities in the past. When we would solve linear equations, for instance, if we look on the left-hand equation, 3x plus 6 equals 3 times x plus 2. After we use the distributive property, we notice the left side is exactly like the right side. You might have written that the answer was identity or infinite solutions. The reason this is an identity is it's true for all values of x. It doesn't make a difference if I put in x is 1, x is 3, x is 1 million, x is 10. The left-hand side of the equation and the right-hand side of the equation are always equal. Versus the right-hand side that you see on the screen, where I have 3x plus 6 equals 3 times x plus 3, the 3x's are going to cancel, leaving you with 6 equals 9. That is not a true statement where it's no solution. So the idea of identities or identity is something that you have experienced in the past, and now we're going to apply it to trigonometry. So an identity is an equation that is true for all values of the variables for which both sides of the equation are defined. In this lesson, you will discover some trig identities by manipulating the graphs of trigonometric functions. In other words, you're going to use identities to make new ones. And you will have to use your algebraic skills and your knowledge of trigonometric representations to prove that these are true. Don't get too worried about the word prove. It isn't going to be a two-column proof, but a series of algebra steps that you will be able to show that the left side is indeed equal to the right. What are the fundamental identities? We briefly discussed them in a previous trig unit in our previous course. You need to have these memorized. These will never be provided to you on a test or a quiz. We will notice some new identities in future lessons, and a reference sheet on some of those will be given to you, but any reference sheet that is ever given to you the remainder of this year will not have the reciprocal, quotient, Pythagorean, cofunction, or even an odd identities on them. You must know them. So here are the reciprocal identities. As a reminder, you can freeze the screen, pause to write these down. What I'm going to spend time doing is showing you why they're true. So let's take the sine of u equals 1 over cosecant of u. All right? Notice here that if I type in the sine of x, and I have to use x on the graphing calculator instead of a u. Okay, that's the graph of the sine x. But now if I graph 1 over the cosecant of x, I get the same graph. That's why they're an identity. They are equivalent. They are both true for any value of x. I won't spend time doing every single identity in this grouping. I'm sure that you catch the drift, and you can also verify them yourselves on your own graphing calculator. But if I wanted to do, for instance, the tangent of x, okay, there's the tangent. It is equivalent to 1 over the cotangent of x. I get the same graph. The next group of identities are the quotient identities, and hopefully this makes sense. If we know that the tangent is y over x, and we know that the cotangent is x over y, we know that the sine, when we talk about the unit circle, is equivalent to the y coordinate, and the cosine is equivalent to the x coordinate. So it should make sense that the tangent is equivalent to the sine over cosine, and the cotangent is equivalent to the cosine over sine. Again, why does this work? If I graph, I already have the tangent of x graphed. Another way that I can represent this is the sine of x over the cosine of x. Again, I get the same graph. Similarly, if I graph the cotangent of x, that is equivalent to the cosine of x over the sine of x. So again, the cotangent of x and the cosine over sine of x, they are true for every value of x. The next group of identities are the Pythagorean identities. And where does this stem from? If I put a triangle on the unit circle and I have my x length and my y length and the radius, since it's a right triangle, I can use the Pythagorean theorem to set up x squared plus y squared equals r squared. As we know from the unit circle, provided that the radius is 1, the x is equivalent to your cosine. The y is equivalent to your sine, and the radius is 1. So cosine squared x plus sine squared x is the main Pythagorean identity you need to know. Hopefully it's something that isn't too taxing to memorize if you know where it stems from. Now, if I take the cosine squared x plus the sine squared of x equals 1 and divide every term by the cosine squared of x, I yield cosine squared x over cosine squared plus sine squared over cosine squared equals 1 over cosine squared. Cosine over cosine simplifies to 1. Using my quotient identity, sine squared over cosine squared becomes tangent squared, and 1 over the cosine squared using my reciprocal identity becomes a secant squared. So 1 plus tangent squared x equals secant squared x is our second main Pythagorean identity. If we go back to cosine squared plus sine squared x equals 1 and divide every term by sine squared of x, I yield cosine squared x over sine squared x plus sine squared over sine squared equals 1 over sine squared. We're going to use identities to simplify this identity. Cosine over sine becomes the cotangent. Sine squared over sine squared is 1. And 1 over the sine squared becomes the cosecant squared. So why do these work? Well, notice if I put in 1, I get a constant function. And if I write in, and I do have to type this in a little bit different on the calculator, if I have the sine of x squared plus the cosine of x squared, notice how it prints. It does write the sine of x squared. I get the exact same constant function of 1. If you'd like to see another one, if I write 1 plus the tangent of x squared that is going to equal the secant of x squared. Same graph. So for every value of x, the cosine squared x plus sine squared x equals 1. 1 plus the tangent squared equals the secant squared, and the cotangent squared plus 1 equals the cosecant squared of x. It's an identity. These are the three main Pythagorean identities. Just know that you can manipulate each of these Pythagorean identities by solving for a specific term. So if I look at sine squared plus cosine squared equals 1, the 1 is by itself. I can give the sine squared a turn. If I solve for sine squared of x, I would have to subtract the cosine squared from both sides. So that is an equivalent Pythagorean identity. Similarly, if I want the cosine squared by itself, I would have to subtract off the sine squared from each of those. So that's what I've done in the next two blue boxes. If I solve for 1, I would subtract tangent squared from both sides. If I solve for tangent squared, I would subtract 1 from both sides. And last but not least, if I solve for 1, I would subtract the cotangent squared from both sides. If I want the cotangent squared by itself, it's equivalent to the cosecant squared x minus 1. So again, the three main ones are on the bullets, but know that the rest of the identities you see up here, it's just from manipulating that Pythagorean identity, and that can be helpful as we do our future work. Now we have the cofunction identities, where we've talked about the sine of pi over 2 minus u equals the cosine of u. So basically what we're saying is, if I take the sine of 90 degrees, it is equivalent to the cosine of 30. Cofunctions mean If I take the sine and the cosine, the tan and the cotangent, the secant and the cosecant of complementary angles, they are the same. So again, if you would like to see why that works, okay, if I take the sine of pi over 2 minus x, that is going to be equivalent to the cosine of x. They are the same graph. And if you think about this, hopefully this makes sense. If I just graph the cosine and the sine, we know that they're sinusoidal, that they both have a similar shape, but all we've done is take the sine curve. I didn't want to do that. Let's undo. All we're doing is taking the sine curve, and we are just moving it pi over 2 radians. So we're just moving it either to the left, or you also could have done to the right in this case, where we can put one on top of the other. So that's why those work. Again, if you would like to see another set why it works, I could do the secant of pi over 2 minus x, and that is going to be equivalent to the cosecant of x. They will be the same graph. And our last group of identities in this video are the even and odd identities, and I've highlighted the cosine and the secant because those are a different pattern than the sine family, the tangent, the cosecant, and the cotangent graph. Basically what this would mean is the sine of negative 90 degrees is the same as the opposite of the sine of a positive 90 degrees. If we are talking about cosine, the cosine of negative 90 degrees is equal to cosine of 90 degrees. If we're talking about tangents, the tangent of negative 90 degrees is equivalent to the opposite of the tangent of 90 degrees, which in this case would be undefined in both cases. So again, why does this work? If I graph the sine of the opposite of x, and I graph the opposite of sine of x, we end up again with the same graph. However, with cosine, if I graph the cosine of the opposite of x, it is equivalent to just the cosine of x. And because cosine x, hopefully this makes sense, has symmetry with the y-axis, it's an even function. That's why that works. By definition of even function, if I put in an opposite of x for x and yield the same function or the same values, it is even. Let me show you tangent. The tangent of the opposite of x is going to be equivalent to the opposite of the tangent of x. So hopefully the graphs have convinced you. You could also use some exact values to help you with your understanding. And we will commence the rest of this lesson with examples in our next class.